All right, so we are talking, and this chapter is on the subject of gravitation. Okay? And there are all these topics that are covered. We'll talk about that. Okay. We'll talk, we'll talk about Newton's theory of gravity. Okay. Mr. Newton came up with this theory in 1687. Okay. And this theory works for weak gravitational fields. Okay. So what does that mean? That works for gravitational fields near the Earth's surface, near the sun's surface, and so on. This theory is not good near, let's say, if you get too close to a black hole. Okay. And also, I mean, if stuff is traveling fast, then you need the special theory of relativity. So we'll be talking about, we will only talk about, okay, so stuff like, so if a satellite is going around the Earth, if it's going close to the Earth, then it's going at about 8 kilometers a second. So we'll talk about stuff moving slowly near weak gravitational fields. Okay, so that's the kind of stuff we'll talk about. All right. Now, this is an approximate theory. If you want to talk about stronger fields, if you want to talk about stuff near black holes, then you want the general theory of relativity, which Einstein came up with over 100 years ago. Okay. So near strong gravitational fields, you need this theory, which is a more precise theory. But that's not the final theory. The final theory is really a quantum theory of gravity. And we still don't have that. Okay. So, for instance, if you wanted to describe phenomenon at the instant of the Big Bang, or just, let's say, 10 minus 35 seconds after the Big Bang, you would need this theory. Well, we don't have that. Okay. Einstein can't do that. For instance, if you wanted to ask Einstein what happens in the middle of a black hole, he can't answer that. Okay, you'd need a quantum theory of gravity. All right, so this is the final theory. This is the most precise theory. We don't have that. This is an approximation. Okay, so there are limits to what this theory can describe. And this is an even, very coarse approximation. This has very limited application, but that's what we're going to talk about. Okay. Now, these things are not easy to do. So, for instance, Newton came up with the theory of gravity in 1687. The next step to go from here to there, see, it took 13 plus 16, 29, 229 years. So to go from here to there, 229 years. Okay. And then, so it's already been 108 years. We got a lot more people working on it, and we're not even nowhere close. Okay. So who knows when we'll have a quantum theory of gravity. Okay. All right, so we're talking about Newton's theory of gravity. Here's Newton's law of gravitation. Okay, and this is what this entire chapter is based on, this one little formula. Okay, what Mr. Newton says is every object attracts every other object with a gravitational force. Okay, so this object attracts this object with this gravitational force, and Newton's third law tells you this guy will attract him with an equal and opposite force. And what Mr. Newton gave us was a formula for the magnitude of this force. Okay, and there's the formula for the magnitude of the force. The magnitude of the force is equal to the gravitational constant times the product of their masses divided by the distance squared. Okay. So, and the distance is measured from the center of gravity to center of gravity, or center of mass to center of mass. Okay. And that's it. Yep. So this is Newton's law of gravity. Now, it turns out that there's only 4 kinds of forces in nature, and gravity happens to be the weakest force. All right, so the strongest force is the strong force, appropriately named. And if it's, I'm just going to give you a feel for it. If it's 1 unit strong, the next force is the electromagnetic force, which is 100 times weaker. The next force is the weak force, which is 1,000,000 times weaker. And here's the gravitational force, which is roughly 10 to the 39 times weaker. Okay. So again, if you got, so here's a simple thing you realize. This is a very weak force. So if you're listening to him, the only way you can listen to him is when all these guys are quiet, right? Okay. So again, this is the weakest force, and if you want to listen to a whisper, all the loud noises have to be quiet. All right, here's another interesting fact. So here, Newton gave this theory of gravity to us in 1687. This fellow, the constant, was very hard to measure. And this guy was not even measured for over 110 years later. This constant was measured in 1800s, and we'll come to that. Okay. So there's the value of the constant. Okay. Now see, this number is very small. So if this, for this force to be large, okay, at least one of the masses has to be large. Okay, so we said the force of every object attracts every other object in the universe. Okay, so you guys are attracting your neighbors. In fact, you're attracting every object in this room. Okay, but obviously you're not falling towards each other. But if I jump off this table, I'll fall towards Earth. So if I jump off the table, I fell towards Earth because Earth attracted me with a strong force. Well, the force of attraction between Earth and me was about 160 pounds. Yeah. The force between you guys is about equal to the weight of one of your hair. So that's how weak this number is. Yep. All right, so the force between these guys is about 10 to the minus 7 newtons. The force between the Earth and you is about 600 newtons. Okay. Because the mass of the Earth is large. Okay. Of course, every object attracts every other object. Galaxies attract each other. This galaxy is attracting that, and so on. Okay, so we saw that the magnitude of the force of attraction between two objects is that product of their masses divided by the distance squared. Okay? Like I said, actually, this is the least accurately measured constant in physics. Yeah. And this was not measured till 1800s by Mr. Cavendish. Yeah. So it turns out that this experiment is called weighing the Earth, because until we knew this constant, we didn't know the mass of the Earth, we didn't know the mass of the sun, and all that kind of stuff. The afternoon that we measured this, suddenly that day, we knew the mass of the Earth, mass of the sun, and all that kind of stuff. Okay. So let's see how this was measured. Okay, so what this experiment shows you is the following. Okay, since I'm recording this, I'll have to. So imagine a metal wire, okay? And then on this metal wire, we'll attach two masses via a rod like this. Okay. Now what you can do is you can torque this thing, you can twist this, you can twist this wire, okay, and calculate the force it takes to twist the wire through an angle theta. Okay. So this will be, we've seen this for the spring constant. This is called the torsion constant. This is the torque you need. The torque would be force times the distance. Torque would be force times distance. Okay. So you can calculate the torque you need to twist this wire through an angle theta. Did you guys understand that? So here's this wire, metal wire. I'm going to put two balls there, and I can find out what force do I need to apply to twist this wire by an angle theta. Okay. And actually, if I twist it and then let it oscillate from the period, I can measure K. I can get K. Okay. So anyway, I know what force is needed to twist this wire through an angle theta. Okay. Now here's what I'm going to do. So I'm going to give you a simplified view. Okay. So I have this metal wire hanging from the ceiling. I have this rod with two masses. And now what I'm going to do is raise from the floor, I'm going to raise a heavy mass, a bowling ball. One bowling ball here and one bowling ball over here. So I'm going to raise from the floor a bowling ball here and a bowling ball here. What is this guy going to do? He'll attract him. What is this guy going to do? He'll attract him. And that will twist this thing through an angle theta. And if it twists through an angle theta, I know what the force must be. I can calculate the force because I've already measured the torsion constant for the wire. That was the idea. Okay. And this force would be equal to G times M1, M2. And even I know how to measure this masses, and the distance is easy to measure. All right, so there's so when you raise these heavy masses, so there's the original little masses, you raise these heavy masses, this heavy mass attracts that mass, so it goes from here to there, and you measure the twist angle. Now, the twist is very small, so Mr. Cavendish was pretty smart. What he did was to put a mirror there and shone a beam of light there, and as this twisted, this beam of light, so the beam of light, he would project the beam of light on a wall far away. And so he could measure this distance and calculate the angle theta. Okay? So this was like a magnifier. Okay. All right, that's how you measure G. All right, so once you measure G, what is the acceleration due to gravity? You guys have measured that? Yeah, so, okay, so the force of gravity on this guy is mg, and that is equal to g, mass of Earth, m, the mass of the object, divided by the radius of the Earth square. You're essentially at the radius of the Earth. Yeah. You guys have measured this. We've known the radius of the Earth for 2,000 years now. Okay. Now that you have measured this, now you can get the mass of the Earth. So, on the afternoon of 1798 is when we found out the mass of the Earth. Yep. So, here's the sun, here's the Earth. Okay. The Earth is going around the sun in a circular orbit at speed v, m Earth v square by r Sun Earth equal to g m mass of the Sun, mass of the Earth. Okay, we knew the Sun-Earth distance as well. Yeah. You just measured this. You well, you don't need that. We know v is the orbital speed of the Earth, which is 30 kilometers a second, but that's equal to 2 pi r Sun-Earth divided by the time it takes for the Earth to go around the Sun. You know this. How long does it take for the Earth to go around the Sun? I'm sorry? 1 year. You know this. So you have g, suddenly you can calculate the masses of all kinds of objects. Okay? All right, so that was a very important experiment. Now, I'm not going to go over the story. All right. So once you add the mass of the Earth, the density of the Earth is mass of the Earth divided by 4 pi by 3 r Earth cubed. That's the volume of the Earth. So you can calculate the density of the Earth, and the average density of the Earth came out to be that number, 5.5 grams per centimeter cube. The density is this is 5.5 times the density of water. Now, if you walk outside and pick up a handful of dirt, the density of that dirt is 2.3 grams per centimeter cube. So this number right away tells you that the Earth is not uniform density. Okay. One little experiment opens up a whole new can of worms. Okay. Eventually, now, so in the 60s or 70s and 80s, here's the density profile. So 150 years later, now we have the density profile. On the surface of the Earth, the density is about 2.5 grams per cc. The mantle has that density. The inner core has density of 14 grams per cc, and so on. Okay, so that's the density profile. Here's a picture of the structure of the Earth. Okay, do you guys know the radius of the Earth? I'm sorry? 4,000 miles, very good. So 6,400 kilometers, 4,000 miles. Okay, so here's the deal. The deepest hole we've dug is about 4 miles. That's 0.1%. So how do we know the structure of the Earth? By the way, this picture is only about 50 years old. So if you were taking a physics class 100 years ago, you wouldn't see this picture. Yeah. So here's how they find this picture. Yeah. It turns out that how does a light beam travel? What kind of path does it travel? A light beam will travel in a straight line. Okay? All waves travel, a wave will travel in a straight line. Okay? But what happens to the light beam when it goes from air to glass? I'm sorry? Yeah. It will refract. It will bend. Okay. Any wave will bend when its speed changes in the medium. Okay. So if the speed of light was the same as in air and glass, it doesn't care if the medium is different, it would travel in the same straight line. Okay? When its speed changes, it bends. Okay? If it gets slower, then it'll bend towards normal, and if it is going faster in the medium, in that medium, then it will bend away from the normal. Okay? And that's refraction. All right, so the bending depends on how much it's slowed down, the speed in that medium, and from its speed, you can calculate the property of the medium. Okay, it's related to density and all that. So here are earthquakes. This is an earthquake wave. It's a wave. It exhibits refraction as well. Okay, and here are seismometers. Okay, so an earthquake occurs, and this wave travels like that to that seismometer. This earthquake occurs. You measured how much later did those earthquakes, those seismometers measured those earthquake waves. So you have all this data, so you can reconstruct this path. You can reconstruct the speeds, you can reconstruct the density. So you had to have many earthquake wave data from many seismometers to construct this picture. Yep. So this was possible only after you had plenty of computation power. Yeah. So this picture, like I said, was made about 50 years ago. Again, if I'm going too fast, let me know. Okay, I'm just going through the punchline. Okay, if you have a uniform body, so let's say like a bowling ball. Okay, and if you're outside the body, the gravitational force of this guy on you, once you're outside the body, he could be a point object or that big or that big. You don't care. The force of gravity will be the same on you. Okay? So for the International Space Station, so let's say this is the International Space Station, you're going around because of Earth's gravity, and now let's say some guy turns the Earth into a black hole, the force of gravity on you is exactly the same. Your orbit will not change. Okay? All right, so once you're outside the object, and again, this is for a uniform density. Okay? If this side was denser than that, then that doesn't work. Okay? The superposition principle, we've seen this before. Okay? So yeah, if you have multiple objects, the force on this guy is in that direction, the force on this guy due to this guy is in this direction. The net force on him is just the vector sum of these two forces. Okay. What is the value of acceleration due to gravity? I'm sorry? Yep. Is an acceleration a vector or a scalar? It's a vector. So which way is that acceleration vector pointing?
It's perpendicular to velocity.
I'm sorry?
It's perpendicular to velocity.
Towards the center of mass of the Earth.
So it's pointing toward the center of the Earth. Okay? Here's the acceleration due to gravity. This is the gravitational field. At the surface of the Earth, the length of this vector is 9.8 meters per second squared. Okay? All right, let me answer this. Hello? Yeah, I'm in class. What? All right. So the length of this vector on the surface is 9.8 meters per second squared. As you go further away, you can see that the magnitude of the vector is changing, but the direction is always towards the center of the Earth. Okay? So, for instance, the radius of the Earth is 4,000 miles. Okay? So, let's go back to this equation. Okay? So, the m cancels. This is where, okay. And if you put the radius of the Earth, you get 9.8 meters per second squared. If you're 4,000 miles above the surface of the Earth, that becomes 2 RE. G becomes 9.8, 10 divided by 4, 2.5 meters per second squared. So on the surface of the Earth, the acceleration due to gravity is 10 meters per second squared. If you're 4,000 miles above the surface of the Earth, the acceleration due to gravity is now 2.5 meters per second squared. Okay, that's what this thing is showing you. All right, so what this notation is, r hat is a unit vector pointing away from the center of the Earth, okay? And the acceleration due to gravity is pointing in the opposite direction. There is the magnitude of the acceleration. R is the distance from the center of the Earth. Okay. Oops, where is that formula? Okay, here, this is the formula I was looking for. Okay, so this gives you the value of the acceleration. I'm not going to derive this. This gives you the value of the acceleration. G naught is 9.8 meters per second square on the surface of the Earth. This is the value of the acceleration at a height h above the surface of the Earth. Okay. So G at this location. Okay. So if h is equal to re, this would be 1. 1 plus 1 is 2. G naught by 4. Okay. 10 divided by 4. So at a height h equal to r, it would be 10 divided by 4, 2.5 meters per second squared. And anyway, here are the values. Okay. So this is in kilometers. The radius of the Earth is 6,400 kilometers. So at about 7,000 kilometers, you see, G is 2.25 meters per second squared. So again, acceleration due to gravity decreases as you go high up. But you have to go fairly high, comparable to the radius of the Earth. So here's an interesting side story. Okay, so we'll do a couple of pieces, a couple of things. Okay, so here's a scale in your bathroom. You stand on the scale. What are the two forces on you? Well, the force of gravity. And then the scale is pushing you up. Yeah. And that's why you're not going through the scale. And this force is equal to the force of gravity. Okay? So Fn is your apparent weight. Okay. So the hair on top of your head, gravity is pulling it down. Your head is pushing it back with the same force, and that's why the hair feels heavy. Okay? All right, that's your apparent weight. Okay, now let's do the following. Let's say you are going in a circular path. What makes you go in a circular path? I'm sorry? Okay, so let me rephrase this. Are you accelerating? Like you're going in a circular path at constant speed. Are you accelerating? Yeah, you have a centripetal acceleration, v squared by r. And so you need a force, a centripetal force, which is equal to mv squared by r. Yeah? So you need that. All right, so now let's do the following. So we'll put you, so this is a top view. You're on the Earth. You're at the equator. And now let's put you on a scale on the equator. Okay, at the equator, you're going at about 1,000 miles an hour. Here's how I know this. Okay, you're going around in 24 hours. 4,000 miles is the radius, 2 pi r. 2 pi is 6. 6 times 4 is 24,000. 24,000 divided by 24 hours is 1,000 miles an hour. So you're going at 1,000 miles an hour. You need a centripetal force. What is the centripetal force on you? Your mass times v squared by r. Where is that centripetal force coming from? the force of gravity. Except that the force of gravity is quite large, much larger than that, so there's this normal force. There's the centripetal force. So you can see that when you're at the equator, this force is less than the force of gravity. Okay, your apparent weight, Fc, is Fg minus Fn. Fn is Fg minus Fc. Fc is mv squared by r. So your apparent weight is not your real weight. Okay. When will this be zero? Oops. Is there any location on Earth where this will be zero?
North Pole and South Pole?
There you go. On the North and South Pole, you're not moving. And you want to measure your true weight, then you just go to the poles. This will equal that. So now let's do the next interesting thing. Okay. Let's just speed up the Earth. It's going at 1,000 miles an hour. Let's speed it up. You speed it up, this increases. Your apparent weight decreases. The Earth takes 24 hours to go around. Okay. Now, if you speed it up such that it takes 90 minutes to go spin once, you can calculate your speed. This will equal that. And your apparent weight will become zero. So, if you were at the equator and the Earth were spinning once in 90 minutes, you're weightless. You can go for a walk and go into orbit. Does that 90 minutes sound familiar? Have you heard it anywhere? That's the time it takes for the International Space Station to go around. Okay? So that's an interesting fact there, all right? So your apparent weight or the effective gravity is g times that, and again, if this angular speed becomes 2 pi radians per 90 minutes, this will become equal to g, and that'll become 0. Okay? So your weight, you weigh about 0.35% less at the equator than at the poles. Okay? So a 100-pound person at the poles will weigh 99.65 pounds. All right, so here's a very interesting fact. Okay, let's say I build a tall skyscraper here. What is this angle? Huh? 90 degrees. So everybody says that. Okay, so I'm building a skyscraper here, and we say it's 90 degrees. So I'm going to show you that. So in this room, that's north. So this skyscraper is actually tilted towards the North Pole. So every building on the beach, this building is tilted towards the North Pole. It's not perpendicular to the ground. All right, so let's see that. The only buildings that are perpendicular to the ground are at the equator and at the poles. Okay. All right, so let's see what is the argument for that. Okay, so here's this fellow. The Earth is spinning, he's going around the Earth, right? Okay. So what is the circle he's making? He's going around this circle. So if you're standing here, okay, and you're going around in this circle, and so you need a centripetal force in that direction. Where is that centripetal force coming from? Well, it's due to the sum of all the forces acting on you. Okay, so you need a centripetal force along that, in that direction, along that chord. Okay. And this diagram, by the way, is so let's say now we're building a building. So what do? You hang a plumb bob. So you're hanging a plumb bob, and okay, so there's a force of gravity acting on him like that. He's going around in a circle, remember, like this, and so you need a centripetal force on him like that. Okay, so the Earth force of gravity is in this direction, and this guy is pulling him upward. The spring is pulling him upward. Well, he's not quite pulling him upward. He's got to pull him like that, because this force plus this force is equal to that force. So you see this plumb bob is actually in that direction. And that's the direction in which you're building the building. So every building in the northern hemisphere is tilted towards the North Pole. And every building in the southern hemisphere is tilted towards the South Pole. So the only vertical buildings are at the equator and at the poles. And this is non-trivial. Okay, so here are the numbers. All buildings are built aligned along this deviated direction. For the tallest building, this represents a deviation of a few feet at the top. I mean, let's say roughly New York and stuff. Yep, go ahead.
Wouldn't the buildings at the equator be horizontal?
I'm sorry?
Wouldn't the buildings at the equator be horizontal?
No.
Based off this diagram?
No, so the equator at the equators, this guy is going in a circle like that. The centripetal force is directly towards the center.
Oh, okay.
Yeah. Okay. I thought this was very interesting when I first learned about it. Now here's something Mr. Newton realized, or Newton proved, and this proof is not easy, but anyway, if you have a shell, let's say this is a basketball, and this was you inside the basketball. Mr. Newton asked the question, well, okay, this piece is attracting you in this direction, this piece is attracting you in this direction. The question is, what is the net force on you due to the basketball? And Mr. Newton showed that for a uniform shell, if you're inside the shell, the net force on you is 0. Okay. All right, well, so let me ask you this then. Let's say the Earth is uniform meaning the density is radially uniform. Again, don't worry about the details. What is the force on you at the center of the Earth?
Wouldn't it be 0?
Very good. Okay, so here's what was happening in his head. What he did was, without realizing, broke the Earth into shells. The force of this shell on you is 0. The force of this shell on you is 0. The force of this shell is 0. The force of this shell is 0. The force of that shell is 0. So when you're at the center of the Earth, the force on you is 0. Okay, so if you are here, this shell has 0 force. The only thing that is attracting you is this mass of the Earth. When you're here, only the mass underneath your feet is attracting you. So as you go deeper and deeper, less and less mass is attracting you, and the force on you is getting less, smaller and smaller, till you get to the center of the earth when it's zero. And it turns out that this force on you, so the force on you, so if you measure this as x, the force on you is exactly like that of a spring. And the spring constant is, of course, related to the mass of the earth. Okay, so, and there's the spring constant. There's R, which is, R is measured from the center of the earth. Okay, and there is the spring constant. You guys did this experiment when you have attach a mass to a spring. And you set it in oscillation. It oscillates with a period related to the spring constant. The period was 2 pi square root of m divided by k. It was related to, but it executed a simple harmonic motion. So here's the deal. Let's say you dig a tunnel through the earth. Again, this is not, we won't be ever doing this anytime soon. Remember, the deepest hole we've dug is, 4 miles. We barely scratched the surface. But let's say if we dug this tunnel and you stepped into the tunnel. If you stepped into the tunnel, you just oscillate back and forth, just like that mass attached to the spring. If you dug this tunnel, it turns out that you'll be going at 18,000 miles an hour here, back to 0 miles an hour, 18,000 miles an hour. The time it would take you, the time for one period would be 90 minutes. What is 90 minutes?
No time it takes the International Space Station to go around.
Exactly. And so that motion and this motion are related. This motion close to the surface of the earth is this simple harmonic motion plus this simple harmonic motion. All right. So fun stuff. Okay, there's the period. So you can calculate the period using this formula and put that spring constant. Okay? And it works out to that. All right. What is the formula for gravitational potential energy? You guys remember? We talked about it in chapter 6.
PM
MGH or MGY, okay, whatever you want to call it. Okay, this formula is good when you're close to the surface of the earth, when G is constant. But you just saw a minute ago that as you go further and further away, G is not constant. Okay, so this formula is not good if you, let's say, if you jump 1,000 miles. Now, you don't often jump 1,000 miles, and so you're happy with this formula. But let's say if you are able to jump 1,000 miles, then you need a more accurate formula for the potential energy. And I'm not going to derive it, so the accurate formula for the gravitational potential energy for small objects, here's the mass of the earth, this is your mass divided by R. R is the distance from the center of the earth to that object. Okay? So the gravitational potential energy of this satellite is negative Gm mass of the earth divided by R. Okay? Here's the more accurate formula. And again, you have to use this if you find yourself going distances comparable to the radius of the earth. If you are very close to the surface of the earth, then this is good enough. But if you make interplanetary journeys, then you have to use this. Okay? This is a pain in the neck to use for simple calculations. But if you wanted to calculate the potential energy of the solar system, it is the potential energy of this pair plus this pair plus this pair, every independent pair. Okay? So there is the potential energy of this system of particles. Okay, do you guys need a break? Or should we keep going? Anybody need a break? I'm sorry? Okay. What is escape velocity? What does that mean? Okay, so let me do this. Okay, so I'm going to toss this object. It rises up and falls back. I toss it at a greater speed, it rose up further and fell back. The question is, can I throw it at a speed such that it will never come back? And that is escape velocity. Okay? So I can throw it at a speed such that it never comes back. Now, if I climbed up on a tall ladder and threw it from there, will this escape velocity be the same as this? It'll be smaller. Okay, so the further away you are, okay. Now, here's another thing. So I throw this object with an escape. So, by the way, from the Earth, it's 11.2 kilometers per second. Okay, so ignoring air resistance. If you throw an object at 11 kilometers a second from the surface of the Earth, it'll escape. By the way, the direction does not matter. Okay, you can throw it at that speed in any direction and it'll escape. So here's an interesting fact. The space station is going at 8 kilometers a second. See, any bound object, the space station is bound to Earth, its speed is less than the escape velocity. Okay, and that's why it's bound. Okay, so the escape velocity from at this distance from this object is given by that formula. Okay, so the escape velocity from the surface from this object is that. Okay, let's take this object and squeeze it. I'll take the Earth and just squeeze it. What happened to the escape velocity from the surface of the Earth? You decreased R, escape velocity got bigger. I'm going to squeeze it more. It got bigger. Can anything travel faster than the speed of light? No. So you squeeze it to a point where this escape velocity becomes equal to the speed of light. You turned it into a black hole. So you can take any object and make it into a black hole. All you have to do is squeeze it to the right radius. You can turn Earth into a black hole if you squeeze it to about that size, the size of a marble. You can turn the sun into a black hole if you squeeze it to a radius of 3 kilometers. 3 kilometers is from here to 95. All right, so here's the escape velocity. Here's the escape velocity from the surfaces of various objects from the Earth, from Venus, and so on, and from Jupiter, from the moon, and so on. Okay. I'm not going to go over this. The atmospheric, so we have an atmosphere, the moon doesn't have an atmosphere. And the reason the moon doesn't have an atmosphere, the escape velocity is small enough, and if there were any gas, it will be warm enough where all the gas molecules would escape from its gravity. Yeah. So you go to the moon and release, well, we don't have helium in our atmosphere. That's because helium is light enough where it'll go fast enough at this temperature and escape. Okay, but you can go to the moon, take a bunch of oxygen and release it on the surface of the moon, and it'll all escape. Yeah. All right, what is the force of gravity? The force of gravity between these two objects is given by Newton's law, where r is the distance between their center of masses. Okay. That's the inverse square law. As long as the force is like this, okay, so if this is massive, this guy will orbit around him. And his orbits, so for the Earth orbiting the sun, the orbit can only be one of three types, okay? And these are all sections of a cone. So here's a cone, and there are conic sections. As long as the force is like that, the orbit can be either a circle or an ellipse. These are bound orbits, so this is bound to that object. Here's a parabolic object, a parabolic orbit. These two orbits are unbound, so you come from infinity and go to infinity. So this is a parabolic orbit, this is a hyperbolic orbit. Okay. The difference is the total energy of this object is less than zero, the total energy is zero, the total energy is greater than zero. Okay. So Kepler gave us three laws for planetary orbits, which are bound orbits. Okay. And we'll talk about that. So here are Kepler's laws. Okay. So if you have a bound orbit, then it's one of these conic sections, and the probability is higher that it'll be an elliptical orbit. The probability of a circular orbit is low. Okay. So the first law just says all planets have elliptical orbits. It's just a probabilistic statement. Yeah. It's a random thing. So the radius vector drawn, the second law says the radius vector drawn from the sun to the planet sweeps out equal areas in equal intervals of time. So let's say the planet went from here to there in 1 month. That is the area it swept out. In the next month, it'll sweep out an equal area. Yeah, so, and the third law says square of the orbital period of any planet is proportional to the cube of the semi-major axis of the elliptical orbit. Okay, we'll keep it simple. What Mr. Kepler realized was the Kepler's third law says the following. And this was quite amazing. T1 square divided by R1 cube is the same for all planets. So when you're orbiting a heavy object, your period square divided by radius cube is the same.
It's a constant?
It's a constant. What Mr. Kepler didn't know was it was inversely proportional to the mass of the sun. Well, here's the beauty of physics. We have about 500,000 objects orbiting Earth. little objects. That's true for them too. T squared by r cubed is proportional to the mass of the Earth, inversely proportional to the mass. It's the exact same thing for every object. Okay. That's Kepler's third law. The square of the orbital period of any planet is proportional to the cube of the semi-major axis. Okay, we'll come to that in a second. Okay, so first law just says, it's elliptical orbits. You guys can read it. Okay, a consequence of inverse square force law. So again, this is Newton's law of gravity. As long as you have an inverse square law, then the orbit is an elliptical orbit. Now here's Mercury's orbit. Now this is an entire story by itself. So an elliptical orbit would be a closed orbit. Okay? And Mercury should keep going around that orbit forever. Here's the actual orbit of Mercury. The path is precessing. Okay, so it starts off like that and then goes. Now this precession is very tiny. It's absolutely amazing how they even measured it. So since it precesses, that means this is not the exact law. There needs to be correction to that. And when Einstein came up with his general theory of relativity, that's the first thing he calculated. That's the first check he made. He's tested to see if his theory could predict this precession exactly. And this precession is 52 seconds of an arc every 100 years. Yeah, that's tiny, tiny. Here's the orbit of Pluto. Here's an elliptical orbit. The sun is at one foci, the other foci is empty. Okay. And Pluto is the most eccentric orbit. Here's how the orbit of a comet looks like. Okay. Kepler's second law, which says, here's Kepler's second law. This planet, let's say this is the area swept out in 1 month, this is another month, all these areas are equal. That's what Kepler says. Okay. So if you're closer to the sun, you're going faster. When you're further away, you're going slower. So this is the area swept out in this time. Okay. So area swept out per unit time is constant. And Mr. Kepler didn't know this, but what it's saying is it's a conservation of angular momentum. The angular momentum of this planet is constant around the orbit. That's what this is saying. Kepler's third law says the period square divided by the radius cube is equal to that. That's the mass of the sun. Mass of the central object. So how long does the Earth take to go around the sun? 1 year. And what is the Earth-Sun distance? What is the Earth-Sun distance?
93 million miles.
93 million miles. So R is about 150 million kilometers. T is 1 year. You can put these numbers and calculate the mass of the sun. Remember, some fellow measured this for you in 1800? You can calculate the mass of the Earth. Here's the Earth, here's the space station. How long does the space station take to go around the Earth? 90 minutes. Its orbital radius is the radius of the Earth, 6,400 kilometers. You can calculate the mass of the Earth with that data. Okay. You should do it. Okay. Right, so here the amazing part. So Kepler didn't know that the constant was related to the mass of the sun. But, you know, he knew the 9 planets, he knew their orbital period, their orbital radius, and see, he calculated that for all the planets. And he got the same number. That's Kepler's third law. Okay. All right. This fellow here is falling asleep.